We will be looking now at what I'd call the random walk in 3 dimensions. Okay, what I mean by random walk is basically what you'd expect a molecule to be doing in a gas. So if you just imagine one particle of the gas, and you imagine what happens as it moves through the gas. So I'm just going to represent the displacements by small vectors. So it's going to go in one direction with a certain velocity v1. It's going to collide with another particle. It's going to move another distance. Might go third one, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 14th, 15th, 16th, 17th. Okay, anyway, I mean, you'd have as many displacement as you want and as small or large as you want. So we're going to call these displacements by vectors small d, and I'm going to say call that this one d1, d2, etc. And in other words, I'm actually going to think about doing actually n steps. And when I'm saying n steps, I'm actually taking to be n to be very large. So I'm doing n very large. But of the order of the number of molecules, if you like. I mean, we're going to see that the number of collisions we have for macroscopic distances is quite large. Again, the idea is to try to come up with macroscopic results from basic microscopic understanding of what might happen to a single particle. In that case, the phenomenon ultimately it relates to is something we call diffusion, which is basically the process by which a gas diffuses into the other. So if you open a membrane and you let the gas slowly go into that, or if you have a permeable membrane and you let the gas go into the another one, or if you open a bottle of perfume, as I said once, and then you wait to see for the perfume to reach. Now, obviously, we're just dealing with the microscopic processes. You might have macroscopic processes in the sense that you can blow uh, uh, the gas, and then that you have a wind, and the wind is a macroscopic phenomenon that would actually push also a particle to another place in the room. So it could push the smell to another place in the room. Now, the question is, after a certain number of these of steps, I'd like to know what is the total displacement of the particle. Now, I'm not interested with the directions. I'd like to know how far did it move from its initial position. In what direction, that's not necessarily something that's relevant to me. Or you might, but when you're thinking about diffusion, after all, if a perfume is open, it's going to diffuse in all directions, but you'd like to know how far it's going to reach after a certain time. Now, the process of diffusion then is basically finding that kind of capital D. Well, what we can write is simply the fact that capital D is simply the sum over all steps of the DIs. But I'm just interested in it, the magnitude of D, so I'm just interested in D. Well, I'm going to square it. Now, why am I doing that? Because basically, again, it's simply the dot product of D times D, which is basically the sum over I. I'm not going to write I completely of DI dot the sum over I of DIs. Now, it so happens that the dot product is distributive. So basically, I could say that D is simply equal to, now I'm multiplying D1 by D1, D2 by D1, D3 by D1, etc. And then I'm multiplying D2 by all the others. So in other words, I'm going to have a number of terms. I'm going to have the number of times Di is multiplied by Di. So D1 is multiplied by D1. And then I'm going to have D1 squared So I'm going to have d1 squared plus d2 squared plus etc. until dn squared. And then I have all the cross terms. So I'm going to have the sum for I going from 1 to n, the sum for j going from 1 to n, but this time as long as I and j are different, of di dot dj. And I get all the terms I can have in D. Now, di dot dj is simply di dj cosine theta, the angle between I and j. I'm going to call it cosine ij. So I could write now, sorry, I'm writing a vector. I'm not supposed to. So I'm going to take my eraser and erase this vector. And I'm going to write, I'm supposed to select again that, and that's d squared, d squared. Now that's equal to the sum for I going from 1 to n of di squared plus the sum over I and j for I different than j of di dj cosine of the angle theta, which is the angle between I and j, between the two vectors. Okay, now I'm just looking at the sum of a very large number of steps, very large. And then I could basically think of the integral as some kind of, the sum as some kind of integral over all this. The steps di are not equal. The cosines between the different angles are not equal, but they follow a certain distribution. Now, what is the distribution of di's? And that's where the free paths are interesting. Well, the question is, what is the distribution of di's? Well, we've seen that the free paths obey distribution. The free paths obey distribution, which was known in the textbook when you read it as a survival equation, which tells you that n is equal to n0 exponential of minus x over lambda, where lambda is simply the mean free path, right? The expression we found in the previous videos. Well, in the previous. Now, what is n? N in that situation, if you want to interpret that, n was the number of particles that undergo a collision up to a free travel x, and n0 is the total number of collisions. I mean, you could think of it as you're sending 10 to the 23 particles, and then you're basically having them travel freely with obstacle in the path. Now, obstacles are themselves, and then you tell yourself, okay, fine. After, let's say, 1 micron, I have 100 particles who collide. After 2 microns, I ended up with 200 particles who collided, etc. And then n is the total number of particles who collided before this. Now, what could I make of that? After all, I'm saying it's a number of particles. But I could think also of it as a number of collisions for a free travel x, for a free path of x. So if the total number of collisions is n0, n is the number of collisions after a distance x. So for a free path up to x. In other words, I could interpret things in a different way. I could say n is number of collisions up to, for a free path. So I'm going to say for a free path going from 0 to certain distance x, and n0 is the total number of collisions. But then if you come and think of it, if I compare to what I'm doing, that's the total number of steps, and this is the number of steps which have that kind of length. So it's a number of steps whose length is between 0 and x. And you've seen also that to calculate the mean free path, I could say essentially, and that's basically the way you calculate averages, you'd say that the mean free path is simply the integral of x dn from 0 to infinity divided by the total number of particles or of steps. So you've got a number of steps n0. Some of them have different lengths from 0 to infinity. The number is step width times the number of particles that have step x divided by the total number of steps. And keep that in mind, because that's something we're going to use later on. So this being said, as a reminder, let's go back to our expression. We found then that d squared equals to sum of I of di squared plus sum over I, okay, going from 1 to n, sum over j, going from 1 to n, with I different than j, of basically di dj cosine theta ij. Fine. Now, what I need to do is a sum. So I'm going to sum here over different lengths, and I'm going to have to sum here over different lengths and over different angles. So it's similar to what we've done with the relative velocity, where I have to do the averages over different things. So I'm going to do first, my first step will be to compute this, and then I'm going to compute that. So I'm going to do that in the next videos.